Today I want to talk about temporal similarity search. Temporal similarity search is a technique that allows for the retrieval of similar patterns or sequences within time series data. There are two types of temporal similarity search that is supported in KDB.AI. One is transform temporal similarity search and one is non-transformed temporal similarity search. Non-transformed temporal similarity search can conduct near real-time similarity search across very fast-moving time series data. And it does this by performing vector search directly on time series columns. So that means there's no need to embed or compress the vectors in an index, for example. And this completely eliminates the pre-computation that is necessary to build an index. It also allows for dynamic searches. We could change the number of points that we are searching at runtime. So instead of searching, for example, 30 points, we could search 1,000 points or 500 points. And this gives us more flexibility to really understand the patterns that we're searching. We could also do outlier search to identify anomalies. For example, in the image below, we have fast-flowing time series data. And we have a query vector A, which is just data over time frame A. And what we find is that the data displays a similar pattern over time frame B and C. And we could use that to figure out what caused A, B, and C to be similar, for example. So we could find the top n most similar results to any time window. Let's compare non-transform TSS to an HNSW ANN index. So for non-transform TSS, we have a memory footprint of 18.8 megabytes, while for HNSW, the memory footprint is 2.4 gigabytes. And we also save the time necessary to build a single index. For non-transform TSS, we don't actually have to build an index. But for HNSW, we have to wait 138 seconds for the index to complete. And what that means is, even though the time for a single similarity search is 23 milliseconds, which is much longer than the 1 millisecond for HNSW, if we account for indexing time, this means non-transformed TSS is going to be 6,000 times faster for a single search and 17 times faster for 1,000 searches. So the thing that determines whether we need non-transformed TSS here is whether we can afford this indexing time. And for live data or fast-moving data, there's not sufficient time to construct an index, so we're kind of forced to use non-transformed TSS. And we get these massive memory gains as well, because non-transformed TSS takes advantage of how data is moving over time in order to store it more efficiently. There are many use cases for non-transformed TSS. One big one is financial market analysis. Let's say we have a lot of real-time data and we want to identify patterns in stock prices, for example. Well, what we could do is we could use this live data to forecast market trends or find outliers. Same with sensor monitoring. Let's imagine we have live sensor data coming in from sensors in IoT devices. Well, we could detect anomalies, we could predict failures, and in general, we could find patterns that allow us to enhance performance. We could also power predictive maintenance applications, because when we see that there is a maintenance issue, we could get a notification in real time. For something like cybersecurity threat detection and prevention, what we could do is we could monitor for unusual traffic patterns. So every time we see an unusual traffic pattern, well, not only can we send a notification because we'll know about it in real time, but we could also find similar times such patterns occurred. And we could, for example, see what actors were live during both times. For something like healthcare monitoring, when we're monitoring real-time patient data, it's really important for us to be able to detect anomalies or certain patterns in heart rate and blood pressure in real time. And we could also use this to predict medical events. If we see a certain pattern occurring and we know that this indicates a problem, well, we'll know beforehand that we need to alert the user, for example. And we could use this to deliver personalized healthcare insights. With transform temporal similarity search, we could actually dimensionally reduce our time series windows by over 99% while maintaining the original shape. So we have a lot of the same benefits as non-transform TSS, but we have even greater memory savings. And transform TSS supports ANN indexing to boost search speed and performance. So our on-disk and in-memory performance spike due to 100x space savings. And we also get this advantage of increased insertion speeds and search speeds despite our memory savings. One thing to note about transform TSS is that the time frame of all these time series windows must be consistent. But we could have varying numbers of samples within each window. So for example, if we had a window of 1 second, we could insert 30 data points, 40 data points, 100 data points inside that window. But as long as all of them are within 1 second, then we can have these massive memory savings because the compressed dimensions are going to be much lower. Some transform TSS technical considerations are we are actually compressing our data, so we are losing information. But as long as our data is slow or medium moving, this is not too much of a problem, because how this works is transform TSS chooses to be lossy in noisy sections of the window. But if we have very fast moving data, everything feels noisy. And one thing we could do to still use transform TSS on fast moving data is smoothing our data out so it's a little less noisy. But in general, transform TSS is great for identifying macro trends on slow or medium moving data, and it's not as effective on fast moving data. For that, you might want to use non-transform TSS. Some use cases for transform TSS include financial and market predictions. So let's say we have a bunch of historical data and we want to analyze early market data indicators against our historical archives. We can steer market forecasts, we can enrich predictive machine learning models, we can basically analyze patterns and see whether our predictions are correct. We could also use transform TSS for marketing optimization. Let's say we have a bunch of user interaction historical data, such as clicks, views, and durations. What we could do is we could uncover concealed patterns, and we can forecast future behavior. And we could do something like determine the best times and situations for ad campaigns to boost engagement. It's really good for uncovering specific patterns in our data that otherwise would be hard to glean. For retail, we could use transform TSS to enhance our analysis of customer buying behaviors. Let's say you're a retailer and you've segmented purchase history data into time windows and processed them with KDB.AI. Well, then you can use similarity searches to unveil subtle search patterns. You could detect seasonal variations. For example, you can search an interesting price movement or a jump in user consumption and see whether you could figure out past times that this has happened and whether you could take advantage of it. You could do something like track evolving customer preferences. There's a lot of things you could do with transform TSS that you could only do because it really gives you these massive memory savings. Otherwise, it'd be very challenging to analyze great quantities of historical data. I really hope this video made temporal similarity search a little simpler to understand. And in the next video, we'll cover some examples and some code for actually using TSS.